An atom glows in the darkness, then vanishes without a trace. This silent flicker is called spontaneous emission, and it is the hidden heartbeat of our technological world. It makes the lasers in your barcode scanner blaze and the qubits in a quantum computer dream. But this process has a bizarre secret. It is not truly spontaneous at all. It is a whisper from what we call empty space. By the end of this journey, you will understand how the nothingness around us actively shapes reality. We will uncover why atoms decay and how the hum of the quantum vacuum powers everything from the light in your room to the stability of matter itself. What does true emptiness mean to you? This silent flicker is a fundamental rule of the universe. An atom in a high-energy state is unstable, like a ball perched at the very top of a hill. It cannot stay there forever. Sooner or later, it must roll down. When it does, it releases its excess energy as a tiny, fundamental packet of light, which we call a photon. This simple act, an excited atom randomly dropping to a lower energy state and emitting light, is spontaneous emission. It happens on its own without any outside trigger. Think of a book balanced precariously on the edge of a wobbly shelf. You did not touch it, no one else did, yet given enough time, the book will inevitably fall. The exact moment is unpredictable, but the fall itself is guaranteed. That is the essence of spontaneity in the quantum world. This process stands in stark contrast to its more famous cousin, stimulated emission, which is the engine behind every laser. In a laser, an incoming photon of just the right energy coaxes an excited atom to decay, producing a second, identical photon. It is a precise, controlled chain reaction, like a perfectly timed domino fall. Spontaneous emission, however, is a solitary, seemingly random event. It was Albert Einstein, back in 1917, who first formally described these two processes. Even he was deeply puzzled by the spontaneous part. What he wondered could possibly cause an isolated, excited atom to suddenly decide, right now, to decay. If nothing is pushing it, what starts the clock? This question pointed to a profound mystery. The atom, sitting alone in what we would call a perfect vacuum, utterly dark and empty, still somehow knows it is time to fall. It is as if the silent, empty room itself is whispering to the book on the shelf, telling it to let go. Einstein's question revealed a crack in our understanding of the world. In the clockwork universe of classical physics, an atom was a miniature solar system. Electrons orbited the nucleus in neat, predictable paths. If you gave an electron a boost of energy to push it into a higher orbit, classical thinking said it should just stay there, like a satellite moved to a new, stable trajectory. Nothing in the equations of Isaac Newton or James Clerk Maxwell suggested it should spontaneously fall back down and radiate light. An excited atom, left alone in perfect darkness, should remain excited forever, a tiny, eternal beacon. This was the expectation, a universe of predictable permanence. Reality, of course, had other plans. Every experiment showed the opposite. Every single excited atom, without fail, eventually decayed. It did not matter if it was hydrogen in a distant nebula or a carefully isolated atom in a lab on Earth. The decay always happened. This was the moment the clockwork universe broke down. The perfect, predictable machinery of classical physics could not explain this fundamental instability. It was a direct signal that a new set of rules, the bizarre and counterintuitive rules of quantum mechanics, were needed to describe reality at its smallest scales. So, if we cannot predict when one specific atom will decay, how do we talk about it? We talk in terms of probability and populations. This is where the concept of an atomic lifetime comes in. You cannot point to a lone, excited atom and say it will decay in exactly 2.3 nanoseconds. But if you have a large, identical group of them, a whole population of excited atoms, their behavior becomes beautifully predictable in a statistical sense. They follow what we call an exponential decay law. Imagine you have 1,000 of these excited atoms. After a certain amount of time, called the half-life, roughly 500 of them will have decayed. You wait another identical chunk of time, and about 250 of the remaining atoms will decay, and then another wait, and 125 decay, and so on. The number of survivors dwindles in a very specific, smooth curve. On a graph, this is a steep drop that gradually levels off, never quite reaching zero. This curve describes the population perfectly, yet for any individual atom in that group, its moment of decay is utterly random. It is like popcorn kernels in a hot pan. You know roughly how many will pop in the next 10 seconds, but you can never know which specific kernel will be next. The exponential law gives us the rhythm of the crowd, while the quantum vacuum holds the secret to why each individual dancer leaves the floor at their own mysterious moment. The popcorn kernels pop at random, but the curve of decay is perfectly smooth. This paradox forces us to abandon the tiny solar system model entirely. To understand spontaneous emission, we must step into the quantum world where certainty dissolves into probability. Here, an electron is not a planet in a neat orbit. It is a blur, a cloud of possibility. Think of it not as a solid particle at a specific point, but as a hazy sphere of influence, a probability cloud that tells us where we are most likely to find it if we look. The nucleus sits at the center, and this cloud has distinct shapes and sizes, which we call energy states or orbitals. An atom in its lowest, most comfortable state is in the ground state. Its electron cloud is compact and close to the nucleus, but when the atom absorbs energy, the electron is boosted into an excited state. Its probability cloud swells and changes shape, like a balloon being inflated into a more complex form. This new configuration is inherently unstable. It is a temporary holding pattern, a high-energy arrangement that the universe seems to frown upon. The electron in this puffed-up cloud is not happily circling. It is in a precarious quantum superposition, a blend of possibilities yearning to return to the simpler, more stable ground. The decay, then, is the sudden collapse of this bloated probability cloud back down to its compact form. And in that collapse, the excess energy is shed as a photon of light. But what governs the timing of this collapse? In pure quantum mechanics, there is no hidden clockwork, no tiny internal mechanism that wears out. The theory only gives us a probability per second for the event to happen. It is as if the atom, every fleeting instant, rolls a die with an enormous number of faces. For most of those instants, the result says, "Stay excited." But eventually, by pure chance, it rolls the one face that says, "Decay now." This is the core of the mystery. If the math only gives us odds, what in the physical reality actually tips the balance? What provides the nudge that makes the improbable event actual? The quantum description sets the stage perfectly, but it leaves the theater dark and empty, waiting for an actor to finally step into the spotlight and begin the show. That die is rolled against a backdrop we have not yet described. For centuries, empty space was just that, empty. A pure and perfect void, a stage where matter performed and light traveled, but which itself was nothing more than a featureless container. This was the classical vacuum, a complete and utter absence. It was the silence between the notes. If you removed every atom, every speck of dust, every trace of light and heat, you would be left with this perfect nothingness. An excited atom placed in such a true void, according to the old physics, would have nothing to interact with. It would be utterly alone, and its mysterious decay would make no sense at all. But the quantum revolution did not just change our view of particles, it completely reinvented our understanding of nothingness itself. We now know that what we call empty space, the quantum vacuum, is not empty. It is not silent. It is, in fact, the most vibrant and active thing imaginable. The vacuum is a seething, bubbling foam of pure potential. At scales so tiny they defy visualization, pairs of particles and their antiparticles are constantly flickering into existence. They borrow energy from the vacuum itself, exist for an unimaginably brief moment, and then annihilate each other, returning the energy loan before the universe can notice the debt. This is not some theoretical fantasy. It is a direct consequence of Heisenberg's uncertainty principle, which tells us that on very short timescales, energy cannot be precisely defined. This allows for these temporary violations of energy conservation, giving birth to what we call virtual particles. They are virtual not because they are not real, but because they are transient, unmeasurable directly. Their effect, however, is very real. This endless, frantic dance of creation and destruction means the vacuum is filled with a background hum of energy, the zero-point energy field. It is a quantum symphony playing at every point in space all the time. Picture the surface of a pot of water just before it boils. You see tiny bubbles forming and collapsing constantly, a froth of activity where nothing seems stable. That is the quantum vacuum. It is never still, never silent, never truly empty. The atom we thought was isolated is in fact immersed in this chaotic sea of fluctuating energy. It is constantly being gently probed, tickled, and whispered to by this vacuum foam. So when we ask what nudges the excited atom, what provides the probabilistic push for its electron cloud to collapse, we are no longer looking for a hidden clock inside the atom. We are looking at the environment. The atom is not decaying in a void. It is decaying because it is coupled to the infinite, whispering activity of the quantum vacuum. The spontaneous emission of light is in its deepest truth a stimulated emission. It is just that the stimulation does not come from another photon we sent in. It comes from the ghostly, fleeting vibrations of empty space itself. This background hum is the universe's lowest possible energy setting. We call it zero-point energy. Even if you could cool a region of space to absolute zero, the temperature where all classical motion stops, this quantum activity would still remain. It is the irreducible vibration of the vacuum itself. The fields that fill all of space, like the electromagnetic field, can never be completely still. They are always jittering, always fluctuating around a baseline that is not zero. Think of a guitar string. Even when it is not being plucked, if you look closely enough with a perfect microscope, you would see it trembling with tiny, thermal vibrations from the heat in the room. Now imagine you could cool that room to absolute zero. All the heat-induced vibrations would vanish, but the string would still not be perfectly motionless. A deeper, more fundamental trembling would persist, driven not by temperature, but by the quantum rules of reality itself. That is zero-point energy. It is not a mathematical trick. It is a physical, measurable feature of our world. The proof comes from a remarkable phenomenon known as the Casimir effect. Take two perfectly smooth, uncharged metal plates and place them incredibly close together in a vacuum, just a few nanometers apart. Classically, in a truly empty space, nothing should happen. They should just sit there, but in our real quantum vacuum, something extraordinary occurs. The seething sea of virtual particles includes photons of all possible wavelengths. However, the narrow gap between the plates restricts which wavelengths can fit. Only certain vibrations are allowed in that confined space, like only certain musical notes can resonate in a tiny pipe. Outside the plates, all wavelengths are possible. This creates a pressure difference. There are simply more virtual particles, more quantum fluctuations, pushing on the outside of the plates than exist in the gap between them. The result, the plates are gently but measurably pushed together by the pressure of nothingness. This is not theory. It has been demonstrated in laboratories. The silent hum of the vacuum exerts a real physical force. Every atom, every particle, every bit of matter in the cosmos is perpetually immersed in this ocean of zero-point energy. It is the ultimate background static of the universe, a never-ending whisper that permeates the very fabric of space. an excited atom is not decaying in silence. It is surrounded by this infinite chorus of possibility, and it is listening for the right note to begin its fall. The plates in the Casimir experiment are pushed by the whispers of the vacuum. But how exactly does a whisper cause an atom to glow? The connection lies in a concept called a perturbation. In physics, a perturbation is a small, external disturbance that nudges a system, pushing it from one state to another. For our lonely, excited atom, the quantum vacuum provides a never-ending rain of these tiny nudges. The electromagnetic field that fills all of space is not a static grid. Because of zero-point energy, it is in a state of constant, random fluctuation. Think of it as an invisible ocean with a surface that is never calm. Even on the stillest day, the water ripples with tiny, unpredictable waves. An excited atom is like a perfectly balanced marble sitting on a curved plate. Left in absolute stillness, it might stay balanced indefinitely, but place that plate on the floor of a subway car where there is a constant, subtle vibration from the tracks, and the marble will eventually be shaken loose. The atom's excited electron cloud is that marble. The quantum vacuum is the subway. Every random fluctuation in the electromagnetic field is a tiny jostle, a microscopic vibration passing through the atom. Most of these fluctuations are useless noise, vibrations at the wrong frequency, like someone shouting in a language you do not understand. They jiggle the atom but do not trigger the decay. The atom simply ignores them, but the vacuum produces every possible frequency. Sooner or later, by pure chance, a fluctuation will come along with exactly the right frequency, the precise note that matches the atom's own natural resonance. This is the magic moment, when a vacuum fluctuation matches the energy difference between the atom's excited state and its ground state. It acts as a catalyst. It provides the precise, gentle nudge needed to stimulate the decay. In that instant, the electron cloud collapses and a photon is born. This is the breathtaking revelation. Spontaneous emission is not spontaneous at all. It is emission stimulated by the hidden activity of empty space. The vacuum itself contains the ghost of every possible photon, and when the right ghost brushes against the atom, it becomes real. So the randomness we observe, the unpredictable moment of decay for a single atom, is not a flaw in the theory. It is a direct reflection of the inherent randomness of the quantum vacuum's fluctuations. We cannot predict which specific fluctuation will be the right one, just as we cannot predict the exact pattern of ripples on a pond in a light rain. But we know the rain is always falling, and we know that statistically a ripple will eventually hit the lily pad just right. The atom waits, immersed in the silent storm of nothingness, until the perfect, random whisper tells it is time to let go and shine. That perfect, random whisper has a mathematical signature. Physicists needed a way to translate this quantum conversation into a precise prediction. A formula that could tell us exactly how fast a population of excited atoms will decay. They found it in a powerful concept known as Fermi's Golden Rule. Do not let the name intimidate you. At its heart, this rule is a beautifully simple statement about probability and opportunity. It tells us that the rate at which an atom decays, its probability per second to emit a photon, depends on two crucial factors. First, the strength of the atom's connection to the vacuum's whispers. Think of this as how good a listener the atom is. Some atomic structures, with their specific electron cloud shapes, are exquisitely sensitive to the vacuum's fluctuations. They are like finely tuned antennas, perfectly designed to pick up the faintest signal from empty space. The second factor is far more profound. It is the density of available states for the newborn photon. This is the rule's masterstroke. When the atom's electron cloud collapses, it gives birth to a particle of light, but that photon cannot be born just anywhere in any way. It must fit into the existing fabric of the quantum vacuum field. Imagine the vacuum not as a blank sheet of paper, but as a vast grid of tiny, empty slots. each slot representing a possible home for a photon of a specific energy and direction. Fermi's golden rule says the decay happens faster when there are more of these slots available, more possible homes for the photon to be born into. It is a matter of opportunity. If you're trying to park in a crowded city, you will find a spot much faster if there are 1,000 empty spaces versus just 10. The vacuum provides the parking lot, and the density of states tells us how many empty spaces are available at the exact energy the atom wants to release. This is the quantitative link between the atom and the void. The rule takes the atom's innate sensitivity, multiplies it by the number of available photon slots in the vacuum, and gives us the decay rate. It mathematically confirms that the atom is not decaying in isolation. Its fate is woven into the structure of space itself. The vacuum is not a passive stage, it is an active participant with a specific architecture, and the atom's lifetime is a direct measure of that architecture's welcoming embrace for new light. Fermi's golden rule gave us the mathematics, but science demands proof. For all the elegance of the theory, physicists in the mid-20th century needed a smoking gun, an experiment that would show the vacuum's handprint not just in the decay of atoms, but in their very structure. That proof arrived with a meticulous man named Willis Lamb. In the late 1940s, Lamb and his colleague Robert Rutherford performed an experiment of breathtaking precision. They were studying the simplest atom in the universe, hydrogen. According to the best quantum theory of the time, the Dirac equation, two specific energy states in the hydrogen atom should have been exactly equal. Think of them as two shelves in a cabinet that were predicted to be perfectly level with each other. An electron jumping from one shelf to the other should require no energy at all. But Lamb's measurements told a different story. Using microwave technology refined during World War II, he probed these atomic shells with incredible accuracy. What he found was a tiny but undeniable difference. One shelf was ever so slightly higher than the other. The energy levels were not degenerate, as the theory said. They were split by a minuscule amount. This tiny discrepancy became known as the Lamb shift. It was a crack in the foundation of quantum electrodynamics, the theory of light and matter. At first, it seemed like a failure, but brilliant theorists, including Julian Schwinger and Richard Feynman, realized this was not a failure of nature, but a failure of their model of emptiness. They proposed a radical explanation. The electron in the hydrogen atom is not orbiting in a clean, pure vacuum. It is swimming in that seething sea of virtual particles we described. Specifically, it is constantly buffeted by virtual electron-positron pairs flickering in and out of existence. This cloud of transient charges slightly alters the electric field felt by the real electron. It is as if the electron is trying to move through a medium that is constantly shimmering with ghostly reflections of itself. This interaction, this dressing of the electron by the vacuum, changes its energy ever so slightly. The Lamb shift was the direct measurement of that change. It was the first concrete, irrefutable evidence that the quantum vacuum is not a philosophical idea. It is a physical entity with measurable consequences. The empty space inside a hydrogen atom is not passive. It is an active participant tweaking the energy levels of the atom itself. Lamb's experiment did more than win him a Nobel Prize. It bridged the gap between the abstract mathematics of vacuum fluctuations and the tangible reality of a measured number on a lab instrument. It showed that the whispers of nothingness leave a permanent signature on everything that is. The Lamb shift proved the vacuum whispers, but its voice also powers the light in your home. That soft glow from an LED bulb is a direct, everyday conversation with the quantum vacuum. Inside every tiny light-emitting diode, spontaneous emission is not a mysterious quantum quirk. It is a carefully engineered factory for photons. The magic happens in a special material called a semiconductor, most often a crystal like gallium arsenide. In its pure state, this crystal has a forbidden zone, a gap where electrons simply cannot exist. Think of it as a two-story building. The lower floor, called the valence band, is packed with electrons. The upper floor, the conduction band, is mostly empty. The gap between them is like a no-man's land, an energy stairway electrons cannot easily climb. To make an LED, engineers dope the crystal, adding tiny impurities that create an excess of electrons on the top floor and a shortage or holes on the bottom floor. When you apply a small voltage, you push these extra electrons from the top floor toward the holes waiting below. As an electron crosses the gap and falls into a hole, it must shed its excess energy. This is the critical moment. In this semiconductor material, that energy is released not as heat or sound, but almost entirely as light. The electron's fall is a spontaneous emission event, stimulated by the ever-present quantum vacuum fluctuations within the crystal. Each recombination of an electron and a hole is a tiny atomic decay, producing a single photon. Millions of these events happen simultaneously, creating the steady, cool light you see. But how do we get color? Why is one LED red and another blue? This is where engineering meets quantum design. The color of the light is determined by the size of the energy gap the electron must cross. A bigger gap means a higher energy photon, which our eyes see as blue or violet light. A smaller gap produces a lower energy photon, which we see as red or orange. By meticulously choosing and combining semiconductor materials, scientists can tune this band gap with atomic precision. They are literally designing the staircase down which the electrons will fall, and therefore designing the exact whisper of light that will emerge. So when you flip a switch and an LED lamp brightens a room, you are witnessing a vast, orchestrated chorus of quantum events. You are seeing the direct, practical harvest of spontaneous emission, all made possible because empty space is never truly empty, but always ready to coax matter into giving up its light. An LED produces a gentle, diffuse glow, but a laser creates a needle of pure, concentrated light. The fundamental difference lies in how they each harness the atom's desire to decay. While an LED relies on the random, vacuum-stimulated whispers of spontaneous emission, a laser is built to suppress that randomness and replace it with perfect control. It achieves this through a process called stimulated emission, the very phenomenon Einstein identified alongside spontaneous decay. Here, an incoming photon with precisely the right energy does not just pass by an excited atom. It interacts with it, coaxing the atom to release its stored energy and produce a second photon that is an exact clone of the first. This is not a random whisper from the vacuum. It is a direct, amplified command. The new photon has the same energy, the same phase, and travels in the same direction as the photon that triggered it. It is a perfect copy. To build a laser, you need three key ingredients. First, a gain medium, which is a material filled with atoms you can pump into an excited state, like a crowd of people waiting to be told to jump. Second, a pumping mechanism, which is the energy source that lifts those atoms up, filling the crowd. And third, an optical cavity, which is essentially a mirrored tube placed around the gain medium. This cavity is the masterstroke. It traps the photons, bouncing them back and forth through the excited crowd. With each pass, they stimulate more and more identical copies, creating a cascading avalanche of cloned light. All of these photons become perfectly synchronized, marching in lockstep. This is what gives laser light its remarkable properties, coherence and directionality, allowing it to stay in a tight beam over vast distances or be focused to an incredibly fine point. But within this perfectly orchestrated symphony, spontaneous emission plays the role of an unruly heckler. In the laser cavity, before the stimulated avalanche fully takes hold, a few atoms will always decay spontaneously. They emit photons in random directions at random times, completely out of sync with the growing laser beam. These rogue photons are noise. They represent wasted energy, atoms that decayed without contributing to the coherent beam. They can even start light traveling in unwanted directions within the cavity, so laser engineers go to great lengths to minimize this spontaneous noise. They design cavities with specific geometries to favor the stimulated process. They choose gain materials with energy-level structures that make spontaneous decay less likely, or they pump the atoms so intensely that stimulated emission overwhelmingly dominates before spontaneous decay has a chance to occur. This reveals the dual nature of the quantum vacuum's whisper. In an LED, it is the entire engine, the gentle nudge that creates useful light from chaos. In a laser, that same random nudge is an enemy to be defeated, a source of inefficiency that must be engineered into silence so that a purer, controlled light can emerge. The phenomenon is the same, but its value depends entirely on the context, on whether we seek the gentle glow of a chorus or the piercing note of a soloist. The laser's perfect beam shows us how to fight the vacuum's whispers, but what if we could do more than just suppress them? What if we could change the rules of the conversation entirely? This is not science fiction. In laboratories around the world, physicists are doing exactly that by trapping atoms in environments so strange, they can actually stop spontaneous emission from happening at all. The key lies in a revolutionary class of materials known as photonic crystals. Imagine a structure built at the scale of light itself, like a lattice or a honeycomb for photons. This material has a property called a photonic bandgap. Just as a semiconductor has an electronic bandgap where electrons cannot exist, a photonic crystal has a range of light frequencies or colors that simply cannot propagate through it. It is an atomic cage for light. If you try to shine light of a forbidden frequency into this material, it will not pass through. It will be perfectly reflected as if it hit a mirror for that specific color. Now take a single ultra-cold atom and place it inside this engineered void. Cool it to within a fraction of a degree above absolute zero, so its own thermal jitters are nearly frozen away. This atom has a natural frequency at which it wants to decay and emit a photon. If that frequency falls perfectly within the photonic bandgap of the crystal cage surrounding it, something extraordinary happens. The atom is ready to emit, but the photon it wants to create has nowhere to go. Remember Fermi's golden rule: the decay rate depends on the density of available states for the newborn photon. Inside the photonic bandgap, that density drops to zero. There are no empty slots, no allowed homes for a photon of that energy. The vacuum inside the cage has been engineered into silence for that specific whisper. The atom poised to decay finds itself in a new kind of emptiness. It is like a singer opening their mouth to sing a perfect high C, only to discover the entire hall is acoustically designed to absorb that exact note. The sound vanishes before it can even form. In this suspended state, the excited atom cannot release its energy. Its decay is not just slowed, it is suppressed entirely. It is frozen in its excited state not by cold but by architectural design. This is the ultimate control over the vacuum interaction. We are no longer just listening to the whispers of empty space. We are redesigning the room in which the conversation takes place, telling the quantum vacuum which notes it is allowed to play. By caging the atom in this way, we cage the very possibility of its decay, holding a single quantum of light in a state of perpetual, almost a silent scream against an engineered silence. This profound control opens doors to technologies we are only beginning to dream of, from quantum memories that never forget to sensors of unimaginable sensitivity, all by learning how to sculpt the sound of nothingness itself. Engineering a silence for a single atom is a stunning achievement, but we can also do the opposite. We can build a room that amplifies the vacuum's whisper into a shout. This is the domain of cavity quantum electrodynamics, or cavity QED, where we move from sculpting emptiness to conducting a precise duet between light and matter. Imagine the most perfect whisper-quiet room you can conceive. Now line its walls with mirrors of unimaginable reflectivity. mirrors so flawless that a photon of light can bounce between them tens of thousands of times before finally escaping. This is not a room for people, it is a cavity for light, a trap where a single particle of light can be made to linger and interact. Now, into this mirrored chamber, we introduce a single atom, perhaps one chilled to near absolute zero and held perfectly still by magnetic fields or laser tweezers. This setup, a solitary atom caged between two ultra-reflective mirrors, creates a laboratory for one of the most intimate conversations in the universe. The cavity is not empty. It is filled with the same seething quantum vacuum fluctuations as anywhere else, but the mirrors change everything. They impose a strict rule on the light within. Only certain wavelengths, certain notes in the light spectrum, are allowed to resonate between the mirrors. Just as a guitar string only vibrates at specific frequencies, the optical cavity supports only specific modes of light. This fundamentally reshapes the vacuum around the atom. The random sea of fluctuations is now structured, organized into these allowed resonant modes. The atom is no longer bathing in a chaotic hum of every possible frequency. It is sitting inside a carefully tuned resonator. This has a dramatic and controllable effect on spontaneous emission. Remember, decay happens when a vacuum fluctuation of the right frequency nudges the atom. If the atom's natural emission frequency matches one of the cavity's resonant modes, something magical occurs. The density of available states for the newborn photon, which Fermi's golden rule depends on, skyrockets inside that narrow frequency band. The vacuum's whisper at that specific note is amplified tremendously. The atom feels this amplified whisper far more strongly. As a result, its probability to decay, its emission rate, can be enhanced by a factor of 100, 1,000, or even more. It is as if we have taken our singer from an acoustically dead room and placed them in the resonant chamber of a grand cathedral, where their voice is supported, sustained, and powerfully projected. The atom, feeling this enhanced presence of the vacuum, decays almost instantly, releasing its photon directly into the cavity mode, but the control works both ways. If we detune the cavity, if we make its resonant frequency slightly different from the atom's natural frequency, the opposite happens. The density of states for the photon plummets. The vacuum's whisper at the atom's frequency is suppressed within the mirrors. In this case, the atom's spontaneous emission is inhibited, slowed down dramatically, just as it is in a photonic crystal. This is the ultimate knob for tuning reality. By simply changing the distance between the mirrors by a fraction of a wavelength of light, we can switch the atom's interaction with the vacuum from a roaring encouragement to emit to a stifling silence that tells it to wait. This precise control over whether and when an atom talks to the vacuum is not just a laboratory curiosity. It is the beating heart of a new kind of computer. In quantum computing, information is stored in the fragile quantum states of atoms or artificial atoms called qubits. Their greatest enemy is decoherence, the process where these delicate states collapse due to unwanted interactions with their environment, often through spontaneous emission into the uncontrolled vacuum. Cavity QED provides the solution. By placing a qubit inside such a cavity, we can suppress its decay, protecting its quantum information. Or when we want qubits to talk to each other, we can use the cavity as a quantum telephone line. One qubit can emit a photon into the cavity mode, where it is stored briefly before being absorbed by a second qubit on the other side. The cavity amplifies and mediates their conversation, allowing them to perform the entangled logic operations that are the basis of quantum calculation. Here, the vacuum is no longer a source of noise and error. Through the lens of cavity QED, it becomes a tool, a medium we can shape to store, protect, and transmit the most fragile information in the universe. A cavity can protect a qubit, but step outside that mirrored sanctuary and the quantum world grows noisy. The vacuum is not just a whisperer, it is a dissipative environment. In the language of quantum physics, dissipation means the irreversible loss of energy or information from a system into its surroundings. For a delicate quantum state like the superposition of a qubit, this is a death sentence. Decoherence is the name of that process. It is the erasure of quantum weirdness, the moment a particle that was both here and there is forced to pick a side, collapsing into the ordinary, predictable world of classical physics. And what is the primary agent of this collapse for an isolated atom or qubit? Very often, it is spontaneous emission. That gentle nudge from the vacuum that makes an atom glow is the same force that can destroy quantum information. Think of a qubit as a spinning coin, balanced perfectly on its edge, representing a superposition of both heads and tails. This is its quantum state, a fragile balance of possibilities. Now imagine that coin is in a room that is utterly still. It might stay balanced for a long time, but if the room is filled with a constant, random breeze, even the faintest whisper of air, that coin will eventually be knocked over. It will fall to heads or tails, and the superposition is gone. The quantum vacuum is that breeze. Its random electromagnetic fluctuations are constantly probing the qubit. When the qubit is in an excited state, representing a 1 in our quantum code, it is inherently unstable, just like our excited atom from before. It wants to decay to the ground state, the 0. The moment it does so, emitting a photon into the vastness of space, it has not just lost energy, it has broadcast its state to the universe. That emission is a measurement. The quantum superposition, the secret simultaneous existence of both 0 and 1, is irrevocably lost. The qubit is now definitively a 0. This is the core challenge of quantum computing. We are trying to build a cathedral of logic out of spinning coins in a breezy room. To perform a complex calculation, qubits must maintain their superpositions and become entangled with each other, weaving a vast tapestry of interconnected possibilities. This requires time, but the vacuum is always there, ticking like a random clock, encouraging each qubit to decay and shatter those delicate connections. The rate of this decoherence sets a hard limit on how long we have to compute before our quantum information turns to noise. It is a race against the silent hiss of empty space. So building a quantum computer is not just about making qubits. It is first and foremost about understanding and defeating their dialogue with the void. We must learn how to shield them from the vacuum's persuasive whispers, or to design qubits that are simply hard of hearing to its most disruptive frequencies. Every advance in extending qubit coherence time is a battle won against the dissipative nature of the quantum vacuum itself. This is why the study of spontaneous emission is not a niche curiosity. It is the foundational engineering challenge for the next era of computation. To build a machine that harnesses the strange laws of quantum mechanics, we must first learn to tame the hidden activity of the nothingness in which it sits. The vacuum whispers to more than just excited atoms. While we have focused on the emission of light, spontaneous decay is a universal quantum rhythm, a fundamental instability woven into the fabric of matter itself. Consider the very heart of an atom, its nucleus. For many elements, the nucleus is not a permanent, solid core. It is a tense, crowded bundle of protons and neutrons held together by the strong nuclear force. In heavy, unstable nuclei, this bundle can become precarious. The result is radioactive decay, a spontaneous emission event where the nucleus ejects a particle to find a more stable configuration. This is the exact same conceptual process, just playing out on a different stage with different actors. An alpha particle, a cluster of 2 protons and 2 neutrons, can spontaneously tunnel out of a large nucleus like uranium. A neutron inside a nucleus can spontaneously transform into a proton, ejecting an electron and an antineutrino in a process we call beta decay. These events are not triggered by an outside force. They happen because the unstable, high-energy nuclear state is coupled to its own quantum vacuum. But here, the whispering field is not the electromagnetic field. It is the nuclear force fields. The vacuum for the strong and weak nuclear forces is also seething with virtual particles, pions, W and Z bosons, that mediate these interactions. The spontaneous decay of a nucleus is in essence stimulated emission by the hidden fluctuations of these nuclear force vacuums. The nucleus listens to this different kind of quantum static, and when the right fluctuation arrives, it rearranges itself, emitting a particle in the process. This broadening of perspective is staggering. It suggests that every form of instability in the universe, every transformation from a higher energy to a lower energy state, might be viewed as a kind of spontaneous emission, driven by conversation with the active void specific to that force. This leads to one of the most profound questions in all of physics. What about the proton, the seemingly eternal building block of atomic nuclei? Is it truly stable forever, or does it too harbor a secret instability? Most current theories, like the grand unified theories that attempt to merge all fundamental forces, predict that the proton should eventually decay. The process would be unimaginably slow, with a half-life perhaps longer than the current age of the universe, but it would happen. In this speculative vision, a proton could spontaneously transform, decaying into lighter particles like a positron and a pion, mediated by fluctuations of a grand unified force field. If true, it means all matter is ultimately transient, fading over cosmic timescales through the quietest whisper of all. The stability of the chair you sit on, the planet beneath you, even your own body, is not absolute. It is a temporary equilibrium, a long pause in an inevitable conversation between matter and the deepest, most unified quantum vacuum we can conceive. The search for proton decay is therefore the ultimate test of this idea. It is an attempt to hear the faintest possible echo of spontaneous emission, one that would tell us that everything we see is slowly, silently, dissolving back into the hum of the universe. The proton's slow fade would be a quiet end for matter, but the vacuum holds a far more dramatic and final possibility. To understand it, we must look beyond atoms and nuclei to the very stage upon which they perform, the fields that fill all of space. Among these, one is particularly special, the Higgs field. You have likely heard of the Higgs boson, the particle discovered in 2012. That particle is like a splash in the underlying ocean, which is the Higgs field itself. This field is not zero everywhere. Unlike the electromagnetic field, which rests at zero when calm, the Higgs field has a constant non-zero value throughout the universe. Think of it as a kind of invisible cosmic molasses that pervades every cubic inch of space. It is this sticky value that gives fundamental particles, like electrons and quarks, their mass. Without the Higgs field, everything would be massless and zip around at the speed of light. The universe as we know it, with atoms, planets, and life, depends entirely on this field having the specific value it does. It is the foundation of reality's rules, but here is a terrifying question. What if our foundation is not the most stable one possible? In quantum field theory, the Higgs field, like an electron in an atom, can exist in different energy states. The value we measure could be a local minimum, a stable seeming valley, but not the lowest possible valley in the cosmic landscape. Physicists call this a false vacuum. Our entire universe, with all its galaxies and laws, might be resting in a precarious, metastable state. It is like a ball sitting in a small dip on the side of a much steeper hill. It looks stable, it feels stable, and for all practical purposes it is stable. But given a big enough nudge, or through a random quantum fluctuation, that ball could roll out of its little dip and tumble down the mountainside to the true bottom, the global minimum, the true vacuum. This is where spontaneous emission returns on a cosmic, catastrophic scale. In the seething quantum foam of the false vacuum, a bubble of true vacuum could spontaneously form. This would not be a bubble of air, but a bubble of space where the Higgs field has shifted to its absolute lowest energy state. The laws of physics inside this bubble would be completely different. The properties of particles, the strength of forces, everything that makes our universe what it is would be rewritten, and this bubble would not sit still. Driven by immense energy released in the transition, its walls would expand in all directions at nearly the speed of light. Nothing could outrun it. As the bubble wall passes, it would reset the very fabric of reality. Atoms, stars, planets, life, all the structures built upon the old, false vacuum would be instantly and utterly erased, replaced by a new universe operating under alien rules. The process is, in its essence, spontaneous emission for the cosmos itself. A fluctuation in the primordial Higgs field vacuum triggers a decay from a high-energy, false state to the true, lowest energy state. It is the ultimate instability, not of an atom or a nucleus, but of spacetime's own ground state. The trigger could be a random quantum event, a high-energy particle collision, or it might never happen at all. We simply do not know which valley we are in. This transforms our view of the cosmos from a permanent theater to a potentially temporary configuration, a local fluctuation in an eternal field, waiting for the quietest, most random whisper to rewrite everything. That cosmic bubble of true vacuum may never form, but the very possibility forces a profound question about the nature of reality itself. Is the universe a predictable machine, or is genuine randomness woven into its fabric? The answer lies in the quiet decay of a single atom. For centuries, since the time of Isaac Newton, many physicists envisioned a clockwork cosmos. If you knew the exact position and momentum of every particle, the theory went, you could use the laws of physics to calculate their future with perfect certainty. Everything from the orbit of a planet to the flutter of a leaf would be predetermined. This is a completely deterministic universe, a cosmic movie where the ending was fixed at the moment of creation, and we are merely watching it play out. There is no room for chance, only for our ignorance of the complex, interlocking gears. This view suggests a chilling implication for our own lives. If every atom in our brains follows deterministic physical laws, then every thought, every decision, every feeling we believe is our own free choice could simply be the inevitable outcome of a chain of cause and effect that began with the Big Bang. Our sense of self, our will, would be an illusion, a story told by a biochemical machine running a script written 14 billion years ago. The discovery of quantum mechanics and phenomena like spontaneous emission shattered this clockwork dream. When we isolate a single excited atom and ask when it will decay, the equations of quantum mechanics do not give us an answer, they give us a probability. They tell us the atom has a certain chance to decay in the next second, but they fundamentally cannot tell us which specific second it will be. This is not a limitation of our technology or our intelligence. It is a bedrock principle of reality, as stated by Werner Heisenberg's uncertainty principle. The moment of decay is not merely unknown, it is truly undefined until it happens. The vacuum fluctuation that triggers it is not a hidden variable waiting to be measured. It is a genuine random event in the quantum field. This suggests the universe is not deterministic at its core. It is probabilistic. It rolls dice, as Einstein famously disliked, and those dice rolls are not an illusion. They are built into the structure of space-time. So where does that leave free will? The existence of quantum randomness does not automatically grant us freedom. True randomness is just another form of causation, one that is unpredictable rather than determined. If our decisions were simply the product of random neural quantum events, that would not feel like free will either. It would feel like chaos, but the presence of this fundamental indeterminacy does something crucial. It opens a door. It breaks the chain of purely deterministic cause and effect. It creates gaps in the cosmic script where something genuinely new can emerge. In these gaps, perhaps our consciousness, our complex neural networks, can act as more than just passive observers. They might integrate these quantum possibilities, weighing probabilities and outcomes in a way that transcends both pure chance and pure determinism. The spontaneous emission of light from an atom, therefore, is more than a technical curiosity. It is a tiny beacon of ontological freedom in the universe. It is evidence that the future is not entirely written, that at the most fundamental level, reality contains a creative element of chance. This does not prove we have free will, but it removes the most formidable philosophical barrier to it. The cosmos is not a pre-recorded tape. It is an ongoing improvisation, with every decaying atom adding a note of genuine surprise to the symphony. The universe's improvisation is not just a philosophical revelation. It is a vast, untapped reservoir of energy. If spontaneous emission is a leak, a tiny drip of energy from excited matter into the vacuum, then controlling that drip is the key to a new energy paradigm. The frontier lies in two opposite directions, locking energy away from the vacuum's grasp, or inviting the vacuum to help us collect it more efficiently. First, consider the quantum battery. This is not a bigger lithium cell. It is a device that stores energy not as chemical potential, but in the excited states of quantum systems like atoms or artificial atoms. The core problem is the one we have discussed: coherence. A regular excited atom is a terrible battery. It self-discharges almost immediately, its energy lost as a spontaneous photon. A quantum battery would need to protect its stored energy from this fate. The secret may lie in collective quantum states. Imagine not one excited atom, but many, entangled together in a single, giant quantum state. In certain configurations, this collective can become dark to the vacuum. It is as if the atoms arrange their whispers into a pattern of perfect silence. While a single singer's note would escape the room, a whole choir singing in just the right harmony can create a standing wave that the walls cannot absorb. The energy is still there, stored in the collective excitation, but the pathway for spontaneous emission is blocked. The battery is charged, yet it does not glow. To discharge it, you would not wait for a random decay. You would apply a precise quantum control pulse, a command that unravels the entangled state on demand, releasing the energy in a controlled burst. Such a device could, in theory, store energy with near-perfect efficiency for incredibly long times, powering deep space probes or acting as a buffer for renewable energy grids. The challenge is monumental, maintaining that fragile quantum entanglement against all other environmental noise. But the principle is clear: to build a perfect vault, we must first learn to silence the conversation between matter and the void. On the flip side of this idea, we can invite the vacuum to be our partner. Today's solar cells are good, but they are limited. A photon hits a semiconductor, excites an electron, and we capture that electron as current. But if the incoming photon's energy is too high, the excess is lost as heat. This is a massive inefficiency. What if we could design a material where that excited electron decays not through wasteful vibrations, but immediately and preferentially through spontaneous emission of a new, tailored photon? This is the concept of a luminescent solar concentrator. Imagine a transparent panel doped with special quantum dots. A high-energy ultraviolet photon from the sun strikes a dot, exciting it. Instead of losing the excess energy to heat, the dot is engineered to rapidly and efficiently undergo spontaneous emission, re-emitting the energy as a lower energy, say, red photon. This new photon is trapped inside the panel by total internal reflection, like light in a fiber optic cable, and guided to the edges where conventional, ultra-efficient solar cells wait to convert it. Here, we are not fighting spontaneous emission. We are enhancing it, designing materials where the vacuum's whisper is amplified and channeled. We use spontaneous emission as a downshifting tool, converting the broad, chaotic spectrum of sunlight into a narrow, manageable beam of light that our best cells can capture almost perfectly. This turns the vacuum from a dissipative foe into an active collaborator in energy harvesting. Both paths, the silent quantum vault and the chatty light funnel, point to a future where our mastery over this most fundamental quantum conversation reshapes our relationship with energy itself. We move from simply exploiting energy states to architecting their dialogue with emptiness, turning the universe's hidden static into the clean, precise power for tomorrow. But the quantum vacuum's influence may reach beyond the cold precision of laboratories and into the warm, messy heart of life itself. Could the same whispers that make atoms glow and qubits decohere also be a hidden player in the biological world? This is the daring frontier of quantum biology, a field that asks if evolution has learned to harness the strange rules of the quantum realm. The most compelling and controversial evidence points to two astonishing processes: how plants capture sunlight and how birds navigate across continents. In the complex machinery of a plant cell, inside structures called chloroplasts, lies the secret of photosynthesis. Sunlight is captured by an array of molecules, primarily chlorophyll, which absorb photons and become excited. This energy must then travel through a dense forest of other molecules to a reaction center where it is converted into chemical fuel. For decades, biologists assumed this journey was a random walk, a haphazard hop from one molecule to the next, losing precious energy as heat along the way. Yet the efficiency is suspiciously high, almost perfect. How does the energy find its way so unerringly? Some researchers propose a quantum shortcut. They suggest the excitation doesn't just hop randomly. Instead, it exists in a quantum superposition, exploring multiple pathways through the molecular forest simultaneously in a wave-like manner. This phenomenon, called quantum coherence, allows it to sample all possible routes at once and almost instantly find the most efficient one. It is like a traveler who, instead of checking one map at a time, instantly perceives every possible road and chooses the shortest. But here is where spontaneous emission and the vacuum enter the picture. This delicate quantum coherence is incredibly fragile. It would be destroyed in a femtosecond by the noisy, warm, wet environment of a living cell unless something was protecting it. One speculative idea is that the system is so finely tuned that the energy transfer is faster than the decoherence. Another, more radical notion is that the biological structure itself somehow engineers the local electromagnetic vacuum, just like a photonic crystal cavity, to suppress the disruptive whispers that would break the quantum spell. The molecular antenna could be shaped to favor the coherent transfer and discourage spontaneous emission that would waste the energy as lost light. While far from proven, it suggests life might not just tolerate quantum effects, but actively cultivate them, using the architecture of matter to sculpt a quiet corner in the quantum noise where efficiency can thrive. Even more mysterious is the avian compass. Migratory birds like the European robin travel thousands of miles with pinpoint accuracy, sensing the Earth's faint magnetic field. The leading hypothesis involves a protein in their eyes called cryptochrome. When light hits this protein, it can trigger a chemical reaction that creates a pair of molecules with unpaired electrons called a radical pair. These two electrons are quantum entangled, their spins correlated in a way that depends on the angle of the Earth's magnetic field. The theory goes that the bird's visual system can somehow perceive the outcome of this quantum spin state, translating it into a neurological signal, a visual overlay of the magnetic map on the world. But this radical pair mechanism is exquisitely sensitive. The entangled state lasts for microseconds, an eternity in the quantum world, but it must be protected from decoherence. Any interaction with the random magnetic fields from other molecules or from the electromagnetic vacuum itself would scramble the spin information. For this biological compass to work, the protein must shield the radical pair from the very vacuum fluctuations that govern spontaneous emission elsewhere. It must create a local pocket of quantum silence, allowing this fragile correlation to persist long enough to influence chemistry and ultimately perception. If true, it means a bird navigating by starlight is performing a continuous, living experiment in quantum coherence. its very sense of direction relying on maintaining a quantum whisper against the roar of the cellular world. These ideas remain hotly debated. The warm, wet, and chaotic environment of a living cell is the natural enemy of quantum phenomena, which typically require extreme cold and isolation. Many scientists are rightly skeptical, arguing classical physics can explain the observations. Yet the experiments continue, probing for the telltale signatures of quantum effects in living tissue. The pursuit itself changes our perspective. It asks if life, through billions of years of evolution, has stumbled upon tricks that our finest engineers are only now discovering in the lab. Has biology learned to quiet the vacuum's disruptive murmurs in one spot and amplify its useful whispers in another, all to achieve a miraculous efficiency? Whether these speculations are confirmed or not, they forge a profound connection. They suggest the same quantum vacuum that dictates the decay of atoms and the stability of matter might also be a silent architect in the story of life, its hidden activity potentially woven into the very processes that let plants grow and birds find their way home. A bird's internal compass and a leaf's quantum shortcut are invisible to our eyes, just like the vacuum activity they might exploit. This presents our greatest challenge: how do we visualize the unseeable? The quantum vacuum is not a thing you can photograph. It is not made of particles in the conventional sense, but of fluctuating fields and transient possibilities. To share its wonder, we must become artists of analogy, painting pictures with ideas that point toward a truth deeper than any literal image. The most famous of these pictures is the concept of quantum foam. Imagine the fabric of spacetime at scales a billion times smaller than an atomic nucleus. Here, the smooth continuum we perceive dissolves into a chaotic, frothing sea. Tiny wormholes might flicker into existence, connecting distant points before pinching off. Geometry itself becomes probabilistic, bubbling with fluctuations. This foam is a powerful metaphor for the violent activity at the heart of nothingness, a visual shorthand for the seething potential from which virtual particles emerge. It is like looking at the surface of a carbonated drink under a superpowered microscope, seeing not smooth liquid but a frenzied dance of forming and popping bubbles. This is not what the vacuum looks like, because it does not look like anything, but it captures the feeling of its infinite dynamism. Scientists go further, using the language of mathematics to create another kind of vision, the data visualization. Through massive supercomputer simulations, they can model the behavior of quantum fields. The output is not a photograph, but a map of probabilities and energies rendered in vibrant, shifting colors. You might see a tranquil blue region representing a low-energy field state, suddenly erupting with a spike of red and yellow as a virtual particle pair bursts forth, only to vanish a computational instant later. These visualizations are translations, turning equations into intuitive color and form, allowing our pattern-recognizing brains to grasp relationships that pure algebra might obscure. They are the infrared goggles that let us see the heat signature of empty space. Yet even these advanced tools have limits. The truest understanding often requires us to let go of the need for a picture altogether and to appreciate the austere beauty of the theory itself. The equations of quantum field theory are not just calculation tools, they are the precise poem of reality. Their symmetry and elegance describe a universe where something as seemingly solid as mass or as spontaneous as decay emerges from the harmonious interaction of invisible fields. Learning to read that poem, to feel the rhythm of its logic, is the ultimate visualization. It is moving from asking what the vacuum looks like to understanding what it does. This shift is liberating. It allows us to hold the idea of a vibrant, active nothingness in our minds, not as a confusing contradiction, but as a fundamental feature of a cosmos far richer and stranger than our senses alone could ever report. Yet the story of the vacuum's whisper is not the only possible narrative. Science at its most vibrant is a living conversation, not a settled monologue. While the standard model of quantum electrodynamics, with its seething vacuum fluctuations, elegantly explains spontaneous emission and phenomena like the Lamb shift, it is not the final word. A small but dedicated community of physicists challenges this very paradigm, proposing that the trigger for decay might lie elsewhere, in a deeper layer of reality we have yet to fully map. These are not fringe ideas, but serious alternative interpretations that force us to question our most comfortable assumptions. One prominent alternative is known as pilot wave theory or de Broglie-Bohm mechanics. In this view, particles are not ghostly probability clouds, but real, point-like objects with definite positions at all times. What guides them along their paths is a hidden wave, a pilot wave that permeates all of space. This wave does the heavy lifting of quantum mechanics, dictating where the particle is likely to be found. In this deterministic universe, randomness is only apparent, a product of our ignorance of the particle's exact starting conditions. How would this explain an atom's spontaneous decay? The excited electron is a real particle in a real orbit, but it is being subtly guided by this universal pilot wave. The decay event is not triggered by a random vacuum fluctuation, but by the deterministic evolution of this guiding wave function. The moment is still unpredictable to us because we cannot know the exact initial state, but it is predetermined. There is no need for ghostly virtual particles. The emptiness is truly empty, and all the weirdness is packed into the guiding wave. Another intriguing framework is stochastic electrodynamics. This theory accepts the reality of the zero-point energy field, the seething background hum, but it strips away the quantum weirdness of photons and particles. Instead, it proposes that all particles are classical objects being constantly jostled by this real, classical random field. An excited atom in this picture is like a tiny antenna immersed in an ocean of real electromagnetic noise. It absorbs energy from the noise until it becomes unstable and then re-radiates it. The decay is spontaneous only because the driving noise is random, not because of any inherent quantum indeterminacy. These alternatives are mathematically consistent and can reproduce many quantum results. So why are they not the mainstream? The answer often comes down to a matter of philosophical taste and experimental parsimony. The standard model, for all its bizarre abstractions, is staggeringly successful and incredibly precise. It has predicted phenomena like the magnetic moment of the electron to more than 10 decimal places. For many physicists, adding hidden layers of reality, like definite particle trajectories or a classical random field, feels like unnecessary baggage when the simpler, albeit stranger, quantum formalism works so perfectly. Yet the debate is far from trivial. It cuts to the core of what we believe about reality. Is the universe fundamentally probabilistic and participatory, as the standard model suggests? Or is it deterministic and mechanical, with hidden variables waiting to be uncovered? The existence of these competing narratives is a sign of health. It reminds us that our best theories are maps, not the territory itself. They are stories we tell to make sense of the data, and sometimes the same landscape can be described by very different tales. The next great leap in understanding may not come from refining our current map, but from daring to consider that the compass we have been using all along might be pointing in a subtly different direction. The precision of a quantum experiment demands tools of exquisite sensitivity. To measure the spontaneous whisper of an atom, we must build instruments that can see the faintest flash of light and measure the briefest flicker of time. Our experimental toolbox is a marvel of modern physics, designed to catch a single photon in the act of being born. One of the most fundamental techniques is called fluorescence lifetime measurement. The goal is straightforward: to determine the average time an atom spends in its excited state before it decays. But executing it is a feat of timing. Scientists begin with a sample of atoms, often cooled in a trap or embedded in a crystal. They then hit the atoms with a precise pulse of light from an ultrafast laser. This pulse is astonishingly brief, lasting only femtosecond or picoseconds, which are trillionths or billionths of a second. In that fleeting instant, the laser pumps a population of atoms into the same excited state, like a starting gun firing for a crowd of runners. The moment the laser pulse ends, the clock starts. The atoms immediately begin their spontaneous decay, each one emitting a photon at its own random moment. Surrounding the sample are ultra-sensitive light detectors, often cooled to reduce their own noise. These detectors do not just measure brightness, they timestamp every single photon that arrives. By collecting thousands, even millions of these individual decay events, a computer builds a histogram, a graph plotting the number of photons detected against the time elapsed since the excitation pulse. What emerges is the beautiful, predictable curve of exponential decay. The data points start high just after the pulse, as many atoms decay quickly, and then they fall away in that classic smooth decline. The lifetime is extracted from this curve, telling us exactly how long, on average, the excited state persists against the vacuum's nudges. It is a statistical portrait of a quantum crowd, painted one photon at a time. But what if we want to witness the act of a solitary actor? This is where the single photon detector enters, a device so sensitive it borders on magic. Imagine a detector so quiet that the arrival of one particle of light, a single quantum of energy, creates an electrical signal you can measure. Modern versions often use superconducting materials chilled to near absolute zero. At these temperatures, a tiny wire or a special circuit is so exquisitely balanced that the minuscule energy deposited by a single photon is enough to trigger a detectable change, like a single snowflake causing a carefully balanced scale to tip. In a landmark experiment, you could isolate one single atom, perhaps held by laser tweezers in an ultra-high vacuum. You excite it with a carefully aimed laser, and then you wait, the single photon detector poised and listening. Then a click, a single electrical pulse. That is the sound of a vacuum fluctuation whispering to the atom, and the atom answering with a photon that traveled through space and was captured, proving the event occurred. By repeating this process over and over with the same atom, you can even map its own personal randomness, confirming that while you cannot predict the exact moment of any one click, the pattern of many clicks will always trace out the same exponential law. These tools, the ultrafast laser stopwatch and the single photon microphone, transform a philosophical concept into raw data. They allow us to witness the quantum vacuum's conversation not as theory, but as a time-stamped event in a lab log, a direct measurement of nothingness gently shaping the fate of matter. The single photon click in a lab is a whisper, but the silence it requires is a roar of engineering. That profound quiet, the ultra-high vacuum, is not merely a tool for studying quantum whispers, it is the invisible foundation of our modern world. To manufacture the heart of your smartphone or the screen you are watching this on, we must first create a slice of space emptier than the void between stars. Inside a chip fabrication plant, silicon wafers travel through stainless steel chambers where the air pressure is a million times lower than at sea level. This is not about keeping dust out, it is about controlling matter at the atomic level. At such extreme emptiness, the few remaining gas molecules are so far apart that they rarely collide. This allows for processes like molecular beam epitaxy, where atoms are fired in a straight line like a microscopic spray paint to build up layers of material one atom at a time. Without this vacuum, the atoms would scatter off air molecules, creating a messy, useless coating. The perfect crystalline structure of a semiconductor, the razor-thin barriers in a flash memory cell, the nanoscale transistors numbering in the billions on a single chip, all depend on this engineered nothingness. The same principle applies to the thin, hard coating on your eyeglasses that repels water and resists scratches. That layer is often applied through a process called sputtering. Inside a vacuum chamber, a target material is bombarded with ions, knocking atoms loose. In the near-perfect emptiness, these atoms fly across the chamber and deposit themselves in a smooth, uniform film on the lens surface. If air were present, the atoms would react with it, forming a cloudy oxide instead of a clear, protective shield. This pursuit of perfect emptiness is a colossal global industry. The pumps, chambers, gauges, and seals needed to create and maintain these vacuums represent a market worth tens of billions of dollars. It is a silent, clean room revolution. Every time you use a touchscreen, stream a video, or rely on a GPS satellite, you are interacting with devices born in a man-made void. The quantum vacuum taught us that true emptiness is impossibly vibrant, but to build our intricate technological world, we must first learn to mimic a deeper, simpler silence, pushing out the air to make room for the atomic architectures of the future. This marriage of high philosophy and high engineering reveals a beautiful truth. To harness the profound activity of the quantum void, we must first master the art of creating a classical one. That pursuit of perfect silence is just the beginning. The ultimate ambition of quantum engineering is to move beyond suppressing the vacuum's whispers and instead to conduct them with the precision of a maestro. Imagine a future not where we shield quantum systems from empty space, but where we sculpt the emptiness itself, designing bespoke vacuum environments on a microscopic chip. This is the frontier of quantum photonics, where the goal is complete, deterministic control over spontaneous emission. The dream is a perfect single photon source, a device that, at the push of a button, emits one and only one photon, exactly when we want it, with its quantum properties perfectly defined. Why is this so crucial? Our current quantum light sources, even the best ones, are still probabilistic. They rely on spontaneous emission, which means the photon emerges at a random moment. You might get one now, or you might have to wait. This randomness is a fatal flaw for building a quantum internet, a network where information is encoded in the fragile states of individual photons. For unhackable quantum communication using a protocol called quantum key distribution, you need to send a secret key made of single photons to a partner. If your photon source is unreliable, if it sometimes emits 2 photons when you wanted one or none when you needed one, it creates security loopholes and crippling inefficiencies. An eavesdropper could exploit the extra photons to listen in without being detected. The solution is to engineer the vacuum so thoroughly that spontaneous emission loses its spontaneity. We must create a system where the excited state has only one irresistible pathway to decay, and that pathway is opened only by our command. This is achieved by placing an artificial atom, like a quantum dot or a defect in a diamond, inside a microscopic cavity with nearly perfect mirrors. But the engineering goes far beyond just building a tiny box. We must tune the cavity's resonant frequency to match the atom's emission frequency with atomic precision, creating that massive enhancement of the vacuum's whisper we discussed earlier. Then we need to pump the atom into its excited state with a control pulse that is faster than any competing process. In this engineered environment, the enhanced vacuum fluctuations seize the atom almost instantly. The decay happens not randomly, but with near certainty within a predictable, incredibly short window after our trigger pulse. The emitted photon is then perfectly shaped by the cavity, launched into a nanoscale waveguide on the chip with perfect efficiency. This is no longer a light bulb flickering in the dark. It is a quantum faucet that delivers single droplets of light on demand. Integrating thousands of these perfect sources onto a single silicon chip would enable the creation of quantum communication networks with ultimate security, where every bit of a financial transaction or a private message is carried by a photon whose very existence is a quantum event, impossible to clone or intercept without leaving a trace. This future of controlled whispers represents the final step in a long journey, From observing the mysterious glow of atoms to commanding the birth of light itself, one perfect quantum at a time. That silent quantum faucet, engineered to perfection, brings our story full circle. We began with a solitary atom glowing in the dark, a flicker that seemed random and inexplicable. We followed that flicker down a rabbit hole, discovering it was not spontaneous at all, but a response to a hidden conversation. The atom was listening to the seething, vibrant hum of the quantum vacuum, a sea of zero-point energy and fleeting virtual particles that fills what we once called empty space. This whisper from nothingness is the true trigger for the decay of excited atoms, the instability at the heart of light itself. From that fundamental revelation, we traced its echoes across the breadth of our reality. We saw it etched into the precise energy levels of the hydrogen atom in the Lamb shift, proving the vacuum's tangible touch. We harnessed its gentle nudge to create the soft glow of LED lights, and then learned to suppress its randomness to build the piercing beams of lasers. We discovered how this same whisper threatens the fragile dreams of quantum computers, forcing us to build cavities and crystals to sculpt silence. We even dared to wonder if biology has learned to quiet or amplify this quantum murmur in the miraculous processes of photosynthesis and avian navigation. This journey reveals spontaneous emission as one of the universe's most profound bridges. It connects the bizarre, probabilistic realm of quantum field theory, where emptiness is infinitely alive, to the solid, tangible technologies that power our contemporary world. Every pixel on your screen, every secure message sent across the internet, every scan at the grocery store, carries the fingerprint of this dialogue between matter and the void. So here is the provocative thought with which we leave you. You are not separate from this hidden activity. The chair you sit on, the air you breathe, the very atoms that construct your body are all immersed in this ceaseless quantum hum. The stability of matter, the flow of light, the passage of time itself are all shaped by an ongoing negotiation with what we mistakenly call nothing. We are not just living in the universe, we are constant participants in a conversation with the vibrant, whispering vacuum that underlies it all. The next time you turn on a light, remember, you are not just flipping a switch. You are asking the quietest part of existence to speak.